Here we have an example of an exponential function where we are modeling population, not unlike one of the examples we saw in the last video, but this time we actually have a function that we can play with and work some numbers on. So let's read the problem first and let's see get a handle on what we're talking about here. The population of India since 2013 can be represented by the following. P of t, so the population at a given time, P of t equals 1.25 times 1.012 to the t power, where t is the number of years since 2013. And P of t is measured in billions of people. And I put that billions word in red there because, well, first of all, it's important to know what our units are, but also that is a change from what's written on your PDF for your class notes. In the PDF for the class notes, it mistakenly says millions. There's a lot more people than that in India. Billions is the correct term to use here for the units. All right, so that's the situation. We've got a function that models the population in India at a given time in years here. And let's see what they're asking us to identify. Question 5 asks, is this exponential growth or decay? So this is an exponential function. Is this exponential growth or exponential decay, and what does that mean in the application? Because we are multiplying by a number, I've underlined in green just now, by a number that is greater than 1. If we're multiplying by a number that's greater than 1, then our number, as time goes on, is getting bigger and bigger. Multiply by a number greater than 1, and you get something bigger than you had before. That's the basic idea, and each year that passes, the population is multiplied by 1.012, which is larger than 1 and hence represents exponential growth. So in the application, that simply means that we are growing, and we can specify a little more than that, but that comes into the answer of question 6. So let's roll right on to question 6 that asks us, what is the growth rate? And what does that mean in the application? So if we're multiplying by 1.012 each year, then India will have 101.2% of the number of people next year compared to the preceding year. 1.012 is the same number as 101.2%. That means that they're going to have not just 100% of what they had last year, but a little bit more than that, a little bit more than 100% of what they had last year, specifically 1.2% more than they had last year. This indicates a growth rate of 1.2%. So and we can interpret that then in the context of the application. They're going to have 1.2% more people next year than they had this year. And then 1.2% more people the year after that than what they have next year, and so on. Each year will grow. The population of India will grow by 1.2% each year. We can read that from that base number 1.012. Finally, question number 7 asks, what is the initial population? We can find the initial population. Actually, we can read it straight off of the function as it turns out, but I like to get the right mathematical interpretation here and say we can find the initial population of any function by considering a time of 0, because that's the initial time. The initial time is at time 0. And so I've got the explanation here, the population in 2013, because this is the population of India since 2013. So we're not asking what is the initial population, like how many people were in India when the Earth first formed. That's not what we mean by the initial population, but the initial population in terms of this function since we're talking about time since 2013, then the initial population will be the population in 2013. That is at time t equals 0. We plug 0 in for t, for time, and the population at time 0, p of 0, equals 1.25 times 1.012 to the 0 power. And you recall, any number to the 0 power is 1. And then 1 times any number is itself. So that simplifies quite nicely to 1.25. And since the population is measured in billions of people, then that 1.25 doesn't mean 1.25 people. It means 1.25 billion people is the population of India in 2013.